these type of questions that we have are pretty interesting questions. In the first part we have 3 conducting shells. We need to find out the charge on each surface of each conductor. This is hollow, all these 3 shells are hollow, they are not solid spheres. So this S1 is actually like this. This is a highly magnified view of S1. This is the material of S1. All here is the material of S1. This is the inner surface of S1. S1 in. This is S1 out. So let us first find out the charge on the inner surface of S1. I am writing it as S1 in. So the charge on inner surface of S1, to find out that, let us draw a Gaussian surface passing through the body of S1. This is S1, this is the inner surface. We are drawing a Gaussian surface like this. This is a sphere inside the body of S1. This is a closed surface. Since a Gaussian surface should always be a closed surface. Now, the electric field at every point of this surface is 0, because every point of this surface is lying inside the conducting material, and at every point inside the conducting material, the electric field has to be 0 by law of conductors. Therefore, the total flux through this Gaussian surface is equal to 0. Now, as we know by Gauss law, this is equal to Q inside upon epsilon 0. Therefore, the total charge inside this Gaussian surface is 0. Now, there can be no charge in the body of the conducting material. There is definitely no charge. This is again a rule for the conductors. There is no charge inside the body of conductors. It is always present on the surface of the conductors. So the only surface of the conductor available here is the inside surface of this shell. So the total charge on the inside surface of the shell will be equal to 0, since Q inside is equal to 0 for this Gaussian surface. Now, this S1 has a total charge Q. It has a total charge Q. Now this can have this total charge Q on its surfaces only. So the two surfaces that this shell has is the inner surface and the outer surface. The total charge on the inner surface is 0. Therefore, the total charge on the outer surface has to be Q by law of conservation of charge. Therefore, the S1 out comes out to be equal to Q. Now, let us find out the charge on the inner surface of S2. Now, by similar logic, this S2 is again a shell like this. Inside there is total charge Q in this spherical shell S1. This S1, this S1 over here, it has a total charge Q, no matter, it may have it in any fashion, it has a total charge Q inside. So we draw a Gaussian surface again, passing through the body of S2. Again, the total flux through this Gaussian surface is 0. Therefore, the net charge inside should be 0. Net charge inside is equal to charge on S1 plus charge on inner surface of S2. Therefore, S2 in plus the total charge on S1 is equal to 0. Now, total charge on S1 is equal to S1 in plus S1 out, that is equal to Q. Therefore, S2 in is equal to minus Q. So, we get S2 in is equal to minus Q. Now, this S2 has a total charge of minus 2Q. Therefore, minus Q charge will be on outside surface of S2, because it should have a total charge of minus 2Q and it has minus Q on the inner surface. Therefore, it should have minus Q on the outer surface also. Now, by the same logic on S3, S3 in plus total charge on S1 and S2 will be equal to 0 by drawing a Gaussian surface through the body of 3Q. Therefore, S3 in will be equal to Q, because Q plus minus 2Q is minus of Q. Therefore, minus Q, therefore Q charge will be on S3 in. Therefore, S3 in is equal to Q. Now, therefore, by law of conservation of charge, S3 out will be equal to 2Q. So, final answer for the total charge on the 6 surfaces that we have comes out to be equal to 0Q, Q, minus Q, Q and 2Q on the respective surfaces. So, in this question, we learned how to find out the charges on each of the surfaces using the Gauss law. Now, similarly, we have the second question. We have 3 large metal plates which are similar in nature. This has a charge of q, this has a total charge of minus 2q, and this one has a total charge of 3q. We need to find out the charge on each surface. Now this metal plate again is actually a metal plate having two surfaces. The surface here if you look closely at this metal plate, this is actually like this. It has a material body here and it has a surface here and a surface here. We need to find out the charge on each of the surfaces. Let us take the charge on this surface to be equal to x. Therefore, the charge on this surface will be equal to q minus x, because the total charge on the left plate has to be equal to q. Let me write it clearly over here. We have three plates, three identical plates. The total charge on this one is q, this one is minus 2q, and this one is 3q. Let the charge on the left surface of this first plate be x, this will be q minus x. Now, if we have two plates which are close to each other, then I claim that if the charge on this surface is y, the charge on this surface has to be minus y. This is a very important deduction. You should always remember this. Whenever there are two adjacent plates, then on the adjacent surfaces, the charge will be opposite of each other. We can prove this by, these are the two plates, this is the surface and this is the surface we are talking about. If the charge on this surface is y, this will be minus y. Why? Because let us create a Gaussian surface passing through the material of this one and with a edge which is and with a side which is perpendicular to both these plates. Now the electric field outside, if any it is there, it will be in the horizontal direction. Therefore, the flux of that electric field through these two sides will be 0. The electric field over here is already 0. Therefore, the flux through these surfaces will also be 0. Therefore, the total charge inside has to be 0. Therefore, if there is a charge x over here, there has to be a charge of minus x over here. So we now know that the charges on adjacent surfaces are opposite of each other. Therefore, the charge on this surface will be equal to x minus q, and the charge on this surface by conservation of charge, that is minus 2q, has to be equal to minus x minus q, and the charge on this surface by adjacent surface logic will be x plus q, and the charge on this surface will be equal to 2q minus x by conservation of charge, that is 3q. Now we get the charges on the respective in terms of x. So the only thing we need to find out here is now x. So we need one equation. I'll tell you a trick here. The charges on the last two surfaces will always be equal. Therefore, x is equal to 2q minus x, 2x is equal to 2q, and x is equal to q. By putting x equal to q in here, we'll get the charges on each of the surfaces. The important logic we used here was that the charges on the last two surfaces will always be equal. I'll tell you why the charges on the last two surfaces will be equal. This is because, let us consider the three plates over here. The charges, let us consider the material over here. The electric field inside this conductor has to be 0. The electric field in the body of this middle plate has to be 0. The electric field over here, at this point, suppose, due to these two plates cancel because they have opposite charges. Due to these two plates also the electric field over here cancels. Therefore, the only electric field at this point is equal to the charge on this plate, on this surface of this plate, and due to the outer surface of this plate. So the electric field due to this plate over here has to be balanced by the electric field due to this plate in this direction. Therefore, these two plates must have equal charges. So remember this rule for future, these two rules. Whenever there are parallel plates in sequence, there may be more than 3 plates also. The charge on the leftmost surface will be equal to the charge on the rightmost surface, and on the adjacent surfaces the charge will be opposite of each other. So we get the final answer as the charge on left surface of left plate is q, the right surface of first plate is 0, over here also it is 0, here it is minus 2q, this is 2q and this is q. So we see here that q and q are same and these two are opposite of each other. If you do not use this trick, you can also solve this by assuming the charge on this plate to be y, x, y and z. This is total q, this is minus 2q, this is 3q. So the charge over here will be q minus x, this will be equal to minus 2q minus y, this will be equal to 3q minus z. So we have 3 variables, we need 3 equations. So you will get 3 equations by equating the net electric field inside each of the surfaces to be 0. let us take the first plate. In the body of the first plate, the electric field has to be 0. The total electric field over here is due to the charge on this plate, the charge on this plate, and the charge on these two surfaces, and the charge on these two surfaces. Therefore, the total electric field over here depends on the charge on this plate, which will produce an electric field in this direction, and the charges on these plates, which will produce electric field in this direction. Therefore, the total charge on this plate should be equal to the total charge on these plates. Therefore, we can equate it like that: x is equal to q minus x plus minus 2q plus 3q. So you'll get the value of x from this. Then by equating the electric field inside here 0, by equating the total charge on the left side equal to the total charge on the right side, you'll again get an equation in y and then an equation in z. You'll get 3 equations on 3 variables, and then you can solve the answers. But the best way is to use these two tricks to get the answer directly.